All right, let's talk about something incredible. We're going to explore the invisible forces that shape literally everything around us, from a supersonic jet cutting through the sky to the air that's quietly circulating in the room you're in right now. We're talking about computational fluid dynamics, or CFD. This is the revolutionary tool that lets us see, predict, and engineer these complex flows. So let's get into it. So here's how we're going to break it all down. First, we'll look at why CFD is considered a whole new pillar of engineering. Then, we'll take a step back and see what engineers were up against with old-school physical testing. From there, we'll see how CFD became the digital wind tunnel and explore just how wide-ranging its applications are. And this is important. We'll also confront the very real dangers of misusing it before finally looking ahead to the future of simulation. Okay. First things first, let's talk about how CFD completely rewrote the engineering playbook. I mean, we're talking about digitizing physical reality itself. So what exactly is CFD? Well, at its core, it's about using computers to simulate how fluids flow and transfer heat. The easiest way to think about it is this three-step process. It all starts with the math. These are the fundamental laws of physics, like the Navier-Stokes equations that govern how fluids move. Then we hand those equations over to the machine, really powerful computers that solve them over and over again across millions of tiny points in a digital space. And finally, you get the output. These incredibly detailed visual simulations that give us a window into how a fluid is going to behave in the real world. But you might be wondering, why did we even need this? To really get that, we have to rewind the clock a bit and look at the massive brick walls engineers were hitting before the digital age. You know, before the 1960s, if you were an engineer, you had two choices. That's it. You had pure theory, which meant trying to solve all the math by hand, something you could only do for the simplest, most basic problems. Or you had pure experiment, where you had to physically build a scale model and stick it in a gigantic, wildly expensive wind tunnel. There was absolutely nothing in between. And that two-pillar world? Yeah, it was starting to crumble under the weight of modern engineering challenges. As we push toward things like supersonic flight, we hit a wall. I mean, how do you replicate the scorching heat of a spacecraft re-entering the atmosphere inside a wind tunnel? You can't. It's physically impossible. The cost to even try was just astronomical. And on top of that, some of these tests were just plain dangerous for the people running them. It was clear something had to change. And this is where our hero, so to speak, enters the picture. To get around these impossible problems, a whole new way of thinking was born. The digital wind tunnel. CFD became that crucial third pillar of engineering. This chart does a fantastic job of showing why CFD was such a game changer. Just look at data resolution. In a wind tunnel, you get data from a handful of physical sensors. With CFD, you get this rich, dense picture of the entire flow field at millions of points all at once. Or how about iteration speed? Building a new physical prototype might take months. A new digital design, you can test that in days, maybe even hours. It completely changed the speed of innovation. Now, this is a really important point to get. CFD doesn't make theory and experiments obsolete. Not at all. It works with them. It fills in the gaps. It lets us explore ideas that were untouchable before. It's all about synergy. And this image is the perfect way to think about it. We're essentially taking the idea of a physical wind tunnel and turning it into software. By breaking down the problem into millions of tiny pieces, discretizing it, we create this virtual lab that you can take anywhere. Want to see what happens at a different speed or altitude? You're not spending a week recalibrating a massive facility, you're just changing a number in the code. It's like having a wind tunnel on your laptop. The effect this had on the design process is just staggering. The old way, design, build, test, find a flaw, start over, that could take 6 to 12 months for just one cycle. With CFD, you can run dozens of digital tests in that same time. You're iterating in days, not months. You get to a much better, more optimized design way, way faster. Now, this incredible speedup didn't just make things faster. It opened up a whole universe of new possibilities. And the amazing part is, the math that works for a 747 also works for, well, pretty much everything. The applications span every physical scale you can imagine. I mean, just look at this range. At the macro scale, architects use CFD to figure out how wind will whip around a new skyscraper. At the mesoscale, it's the absolute backbone of the entire aerospace industry. You can even go to extreme environments, simulating the flow of molten steel inside a foundry, a place you could never stick a sensor. And then at the microscale, biomedical engineers are using the exact same principles to map blood flow in our arteries or design better artificial heart valves. It really is a universal language of physics.
Okay, so this all sounds unbelievably powerful, and it is. But this is where we have to have a serious talk, because with that power comes a huge amount of responsibility. This brings us to the pitfalls, the traps you can fall into if you're not careful.
This right here is what people in the industry call colorful fluid dynamics. See, modern software makes it incredibly easy to create these beautiful rainbow-colored images that look totally convincing. But here's the scary part. Without a deep, fundamental understanding of the physics and the math underneath, those pretty pictures can be completely and sometimes dangerously wrong.
This quote, every single engineering student should have this memorized. The software is just a tool. At its absolute best, it's only as good as the physics models built into it. But at its worst, it's only as good as the person running it. You can have the best mesh in the world, but if your assumptions about the physics are wrong, you're just getting a very precise wrong answer. The buck always, always stops with the engineer.
So how do you make sure you can actually trust your results? It comes down to two critical ideas: verification and validation. Verification is the first step. It asks, am I solving my equations correctly? This is about bug checking your code, making sure the math is sound. It's about mathematical rigor. But validation, that's the much bigger, more important question. It asks, am I solving the right equations? This is about physical truth. This is where you have to take your simulation and compare it against real-world experimental data to prove your model actually reflects reality. You absolutely need both. And the place where all of these challenges come together, the ultimate boss battle in fluid dynamics, is turbulence. It's just this chaotic mess of swirling eddies across a huge range of sizes and speeds, from big vortices down to microscopic swirls, all happening in the blink of an eye. Trying to accurately capture all of that chaos is, well, it's the holy grail of CFD. To give you a sense of just how insane this challenge is, let's take one of these simplest cases you can imagine, simulating the flow over a single flat plate until it becomes turbulent. To do that, without taking any shortcuts or approximations, you need a grid with 17 million points. And get this, to actually process those 17 million points takes 400 hours on a supercomputer. That's more than 2 solid weeks of nonstop computing for the simplest turbulent flow problem there is. Now just try to imagine what it takes for an entire airplane. The cost is absolutely colossal, and it's why turbulence is still such a monster of a problem to solve. So that brings us to our final question. With these incredible challenges still ahead of us, what does the future look like? And what will it really take to keep pushing the boundaries of what simulation can do? Well, the future really depends on keeping these 3 things in perfect balance. You need the vision. That's the software developers dreaming up smarter, more efficient algorithms. You need the raw power. That's the hardware engineers building the next generation of supercomputers that can finally tackle turbulence head-on. But maybe most importantly, you need the discipline of the operator of the engineer to have the rigor to tell the difference between a pretty illusion and physical truth. When you have all 3 working together, that's when you get the thing at the center: trust. So, as we wrap up, I want to leave you with this question to think about. As the next generation of engineers, you are the ones who are going to push this field forward. The only question is, where are you going to make your mark? Are you going to be the one with the vision for better software? Will you design the hardware that gives us more power? Or will you be the one with the intellectual discipline that keeps it all grounded in reality? Something to think about.